Welcome, everybody. We're so glad to have you with us today. Today, our topic is how many factors. I'm Tony, and I work a lot from my base in Cambridge with teachers in South Africa. And with Caroline, usually we run these monthly workshops. Today, Cynthia is with us.
Hello, yes, my name is Cynthia. Like Tony, I'm also based in Cambridge. And like her, I also spent quite a bit of my working life teaching in schools in Cambridge. But I work with, mostly now with teachers in South Africa. Yes, and what's Tony showing us now is a spiral, sort of indicating our ideas of lifelong learning. That we start off at the bottom of the spiral, and as we go through life, go through first of all the school life, but then after school too, that we learn more things. It might be that perhaps we don't know something, so we need to return to something, or it might be that when we move on from it, that we think perhaps generalizing our knowledge, or then maybe later we find connections to other bits of knowledge. And we find out also, as we go through our lifelong spiral, we find out more applications, and just generally we never stop learning. And that's what we hope for all of you and all of our learners and students that we teach.
So the program for today is based on this idea of starting even with the early years before children are in school. And we have a spiral now in the picture for the school years, from lower primary, upper primary, and then lower secondary, and finally upper secondary. And we're going to be doing some activities that are for primary. I know most of the teachers here are secondary, but we've got some primary teachers. And I want you to see how those same theme, it's all going to be about factors, how we build our ideas and reinforce them as we revisit the same topic, the same theme again and again throughout the school years. So today we're working on multiples, on factorization into prime factors, and HCF and LCM, both for numbers, and then a little bit later for algebraic expressions. We'll investigate some patterns in the powers of primes in this factorization, and how to use powers to find the number of factors. Patterns, notice, that's really important in maths, isn't it? So here are the topics that we're going to deal with today. I've classified them as sort of 10 steps, and starting at the bottom is patterns in multiples, finding prime numbers by something which we call the sieve method, and then the factor bug, the factor tree, and the factor ladder. All of those are started in primary school, and then prime factorization. By this time, we're in upper primary. HCF and LCM, really important when it comes to adding fractions, but in other places too. We'll look a little bit about multiples, cycles, and clock arithmetic, modular arithmetic, and then we'll look at some algebra, and finally we'll look together at a set of questions, all investigating numbers of factors and the powers in the prime factorization. So that's our program for today. Now, the big question is how many factors? So to just take an example, 2,100 and 3,100. Now, we might think the bigger numbers have more factors, but actually that's not true. And in this workshop, we'll see how ideas of multiples, factors, prime numbers, HCF and LCM, and number and algebra, how we learn all these ideas in school. And we'll come to answering the question, which is certainly upper secondary, how many factors, and it depends on this fundamental counting principle, and that underpins probability. So that's a really important concept in mathematics. So let's look at this 2,100. Well, 2 squared times 5 squared is 100. So this is very easy to split into prime factors. 3 sevens are 21, so 2,100. There it is in prime factors, and it's got 36 factors. Now, 31 happens to be a prime number. So 2 squared times 5 squared gives us 100. And when we multiply that by 31, we get 3,100. And that has only got 18 factors. So that's a little taste of what we're going to be doing, but we're going to look at this in all sorts of different ways. Cynthia.
You're going to be looking at patterns on a number grid. So we've given you an example here. This is a 100 square. And you'll see that here we've shaded all the multiples of 6, right? So 6, 12, 18, and so on. And not surprisingly, they do form a pattern on the grid. So what we'd like you to do is to choose on your worksheet any of the other grids that you see and start to shade into multiples. So each grid will have a different multiple. So the first grid is multiples of 2, the bottom right hand, the last grid, multiples of 10. So choose a grid and please have a go at start some shading and have a look at the patterns that you get when you do shade in your multiples. And when you're shading, do see if you can spot any similarities. That's another, as Tony said, we mathematicians like to look for patterns. So what is the same and what is different between any of these multiples that you can spot? And this is something that we have seen this last week that certainly our grade 6 teachers have been happily doing with their learners. It's the beginning of the school year, so everyone's doing number and patterns and multiples and factors. So this has had great success, and it's a very good way of getting the learners started and engaged with their work. If you're working in groups, you can spread the work out between your groups so that it doesn't take too long. And as you can see, some of these patterns look as if they're going down vertically, whereas others are more on the diagonal. And you could ask your learners to explain the patterns they see and just generally to talk about anything they notice. What would they like to tell you about any of these patterns, to get them talking about factors, counting on, patterns.
Yes, and of course they'll be connecting this with multiplication tables, and particularly if you're in primary school with lots of activities, so that they really get to remember their tables by doing activities that help them to fix those numbers, those number bonds, those tables in their minds. So now the next step is to use 100 square again, but this is named after this Greek mathematician called Eratosthenes. I call it the prime sieve. And what we do is we shape this sieve, and what's left behind, we get rid of some of the numbers, and what's left behind is the prime numbers. So on a 100 grid square, circle the number 2. Now that's a prime number, so circle it, and then shade all the multiples of 2. Well, you don't need to shade them, just draw a line through all the multiples of 2, 4, 6, 8, 10, and the 2 times table right up to 96, 98, 100. Now, just draw a line through them, a diagonal line or whatever, horizontal, vertical, whatever. So you just push those numbers out because they are multiples of 2, they won't be prime. And then when you have done that, you see that 2, 4, and 6 are crossed out, but 3 isn't. 3 is a prime number. So you circle 3, and then on this same grid, you now put a line through all the multiples of 3, all the rest of the numbers in the 3 times table. Just score them out with a line. And then you do the same for 5, which is your next prime number. All the multiples of 5, that's quite quick to do. And finally, so you've got 2, 3, and 5 circled, and then circle 7 because that's prime, and cross out all the multiples of 7. So what do you notice now, if you've done that? What do you notice about the multiples of 8, 9, and 10? I'd love to see somebody put something on the chat. What's happened to multiples of 8, 9, and 10? So when you've done all this crossing out, that's you're supposed to be doing, what do you see about the multiples of 8, 9, and 10? So now see where it says they're crossed already. So why are they crossed out already? Yes, they're already crossed out. Several of you are saying this. All of them are crossed out. Yes. Why are they crossed out? Why are multiples of 9 crossed out, for example? 8 and 10 are crossed out because they're... Yes, everybody's finding that they're all crossed out. Well done. But why are they crossed? What are 8, 9, and 10 crossed out? So Mogaladi says 8 and 10 are crossed out because they're multiples of 2, and 9 because it's a multiple of 3, according to Melanie. Everybody's got it now. So look at the numbers that are not crossed out, and what can you say about the numbers that are not crossed out? Now here, I've got here the result for what you've just been doing for the 100 square and for the 200 square. Now the 200 square is done in the same way, with crossing out and circling all the numbers that are not crossed out. The prime sieve picture was done by colouring, and so some numbers are coloured on top of other numbers. So what's happened is the ones that are left white are the prime numbers. Now, what we did, if you remember, was we crossed out all multiples of 7, and that was enough to get all the primes up to 100. If you do the 200 grid, you know, you've already done one, 2, 3, 5, and 7. You only got to do 11 and 13, and you get all of, you've got everything crossed out, leaving only the primes. And you see the primes there are all circled on the 200 grid. Now, why is it that you can stop at 7 and you don't have to do multiples of 11 and 13 when you're looking at the 100 square, and you don't have to go beyond 13 like the next prime, which is 17, when you're doing 200? Why is that? And the answer's actually on this slide, because it's all to do with if you've got two factors, and if one is less than the square root, the other's more. So we know 10 times 10 is 100. So we only need to do multiples of numbers less than 10, because if they're bigger than 10, we've already crossed them out because of the one that was smaller when the two were multiplied, you know, when you looked at multiples. So there we go, the prime sieve, and that's a good thing to do, and your learners to do if they've not done it before.
Right, and another good thing for learners to do that we want you to have a go first to experience is the idea of a diagnostic quiz. Each of the numbers by the choices A, B, C, D, so 4 choices, right? You've got some prime factors making a number. So there are 4 different numbers. They're all expressed in their prime factor form. But which of them do you think is the square number? Is it A, is it B, is it C, or is it D?
What's the point of this diagnostic quiz? It's your formative assessment at the beginning of the lesson.
Yes.
So we're finding out either you're very shy, or
Which is possible.
or
Mhm. Or we need to have another lesson on prime factorization or square numbers, or both, or powers, just power numbers. So this is a very useful way of finding out, as Tony said, what your learners have remembered or can do. But you don't always have to do it at the beginning of a lesson. You could do it at the end, once you have given your learners a chance to experience these types of numbers. You could check at the end, have they understood?
If I was doing this in a lesson, I would expect every single learner to be showing me one finger if it was A, two fingers if it was B, three fingers if it was C, and four fingers if it was D. Okay, and I wouldn't let anybody keep their hands down, right? So if they are not sure, they'll have to guess, but you'll see from looking around the class how much the class understand. At the beginning of the lesson, this is important because you know what your learners, you have a good idea what your learners already know or don't know, and that means that what your lesson has got to provide, if they don't already know it, and you'd hope they did, or you thought they might come to the lesson knowing that, they don't know it, then your lesson, you're quick, you've got to think on your feet and change your lesson a bit. At the end of the lesson, as Cynthia says, you can do it then to see how much they've learnt in the lesson.
So the correct answer is B. When you do this in the classroom, you might, as Tony said, everyone's got their hands up, or they might use a show board or a piece of scrap paper. They might have written on something, or they might use fingers, 1, 2, 3, or 4. What a good ploy is, if you then ask somebody, it doesn't have to be somebody with the right answer, ask them what they think and why. You know, always delve a little bit deeper. Why did they choose that number? And without saying whether they were right or wrong, you can then engage the rest of the class in, do they agree or do they disagree? If they disagree, why? Do they have a reason for saying that is not right? Can they explain to their fellow learners? So this is a brilliant way of getting some discussion going and getting your learners used to justifying their answers. So
I like, Cynthia, I like to ask for A, B, C, or D, 1, 2, 3, 4.
Yes. Yeah.
And then to say, all right, now you answer someone of the learners, you answered A, just tell everybody why you gave that answer. And, it'll happen several lessons. So they'll know I don't really mind if they're honest enough as to say, well, they just guessed. I'll say, oh, you made a guess. Okay. But I'll go through all of them from A to B to C to D and let the learner explain why they gave that answer. And I'll tell everybody else, listen hard, because if you got the wrong answer, I'm going to give you another chance. And then I give them a second chance and see if it makes, if most of the people, when they've heard a little discussion about it, whether most of the people change their mind and pick the right answer. So that's how we use the diagnostic test. All right, so we put that in at the beginning because we were going to go on to, as it were, factors, a lesson on factors. So the factors bug is something that learners like to do. And this bug is the bug for 96. And he's got 1 and 96 as his antennae. And that's what you do. You put 1 and the number for the antennae. And then for the legs, you put on pairs of legs opposite each other, you put a pair of factors that multiplied together give you 96 in this case. So you'll have 3 and 32. Now, would you like to put the rest of his legs on? At the moment, he hasn't got all his legs. Would you like to put the rest of the legs on by drawing pairs of legs to represent all the other pairs of factors of 96? And this is a nice little task for learners to do and to find all the factors. It sort of makes them do it systematically too. It makes sense if they go up, carefully go up on the left-hand side 2, 3, 4. 5 won't be there because 5 isn't a factor of 96, but there are a few more pairs of legs there. Yes, so it's 4 and 24. Somebody else has put 6 and 16. 8 is a factor too. Okay, so your bug should have lots of legs now, and if you count them, you'll know how many factors. Now, the second task here is the tree. Now, on this tree, it's going to show you something similar, but not quite the same representation here for the factors of 96. We start off as 2 times 48. Now, please fill in numbers to replace those question marks. Complete the tree to show the prime factors. This is only prime factors that are going to go on this tree, whereas on the bug, you put on all the factors. Replace the question marks here. And at this stage, of course, we're asking for the learners to have a little bit more understanding of the difference between what is a factor and what is a prime factor. So as we go down the main stem there, we're gradually reducing, and at the ends of the branches, they're only prime numbers that you're going to put in until you get down to something times 1. And finally, on the right-hand side, there's room here for you to do something else, which is often called the ladder method. And it's an algorithm, it's a system, if you like, again, for finding the prime factors. And it's just like the tree, but it's set out slightly differently. So fill in all those question marks there. And again, what we're doing in the tree and the ladder is just prime factors, whereas with the bug, we're finding all the factors. Okay, so here are your answers. You can check your answers now. There's the bug with all his legs, and you can see the list of the prime factors underneath. 1 times 96, 2 times 48, 3 times 32, and so on. In the middle, you see the tree, and on the right, the ladder. And from each one of those, that you can see the factorization, the prime factorization is 2 to the power 5, 2 times 2 times 2 times 2 times 2 times 3. That's your 96. And so let's all be clear about the difference between the primes and the prime factorization and the list of all the factors.
We have a question, and this is from not a secondary school teacher. They would like to hear again, what is a prime factor?
A prime number is a number that is you can only divide exactly by itself and 1. It's got it is a number with no other factors. Okay, so 7 is prime because you can't divide anything into 7 exactly. But say 10 isn't prime because it's got factors 2 and 5. And 12 isn't prime because it's got factors 2, 3, 4, and 6. A prime number is one which doesn't itself have any other factors other than 1. And any number at all, any number can be split into prime factors. So if you see on this grid, you've got 31 circles, that's a prime number. And one of the examples we gave was 3,100. So the prime factors of 3,100 are 31, 2, and 5. And it's 2 squared times 5 squared times 31. So the prime factors are factors of the number but they are themselves prime. So I'm going to go back again to where we were up to, which was Cynthia was going to talk about HCF and LCM.
Yes. Yeah, so these are the HCF, highest common factor, lowest common multiple. And what we are going to do, this from quite of doing the rest of the broadcast, I think, is look at how we can use the prime factorization to find highest common factors and lowest common multiples. So this is a someone's talking. So if we know that the prime factorization of 96 is 2 to the power 5 times 3, as we just worked out on the previous slide, the prime factorization of 30 is quite easy to do, because it's, if we think of factors, it's 3 times 10. They're factors, but they're not, 10 is not prime, as Tony just said. So we need to use either our tree diagram or our ladder method to factorize 30 down. So we get 2 15s, and then 3's into 15 go 5. So we get 2 times 3 are therefore the prime factors that go into 30, and together they make up 30. We don't need any squares or cubes. 2 3's are 6 and 6 5's are 30. So 2 times 3 times 5 is the complete prime factorization of 30. So I hope that together with Tony's previous explanation, that you can see what we mean by prime factors. They're prime numbers, but together they must make up the number we're interested in. So 96 has 2 different prime factors, 2 and 3, but 2 3's don't make 96. We need 2 to the power 5. So we need to get the whole of that factorization together to make the number 96. So now, how can we use this to find, to start with, the lowest common multiple, and then secondly, the HCF? So this is something for you to do.
Think about the answer to this question, the one at the bottom there. What about adding fractions here?
Yeah.
And you'll notice that 30 and 96 are on the bottom of those fractions, which are the numbers we're talking about. So we're going to ask you to add those up in a minute.
Yes, the lowest common multiple of 30 and 96, you were telling us on the chat that it was 480. Yeah, which is true. And you said that the HCF was 6, which is also true. But I'd like you to look at the prime factorization and see how we can get at it from there. Now, the lowest common multiple, as I hope you all know, is the smallest number that both 96 and 30 will go into. So we want a number that contains all the factors, all the prime factors of 96 and 30 with no duplicates. So if we start off with 96, we need 96 there, 2 to the 5 times 3. So there's 2 to the 5 times 3. And then we compare it with 30 and see, is there anything, are there any factors in 30, any prime factors that we haven't yet included? We've got a 2 because we've got 2 to the 5, so we've got plenty of 2's. We've got a 3, but we haven't got a 5. So we need to multiply our 2 to the 5 times 3, which is our 96. We need to multiply that by 5 to get our 480, because it needs to be a multiple of both numbers. It must a multiple of 30, so we need the 5 in there, and a multiple of 96, so we need the 2 to the power 5. Now, the highest common factor, a factor, has to go into both numbers. So a factor needs to be in both these numbers that we're looking at, 96 and 30. And it needs to be the biggest we can find. Well, 2 is definitely a factor of both. We can see that. We've got a 2 in both of these prime factor compositions here. And we've got a 3 in both. But we don't have a 5. 5 is not a factor of 96, so we can't have 5 as part of our highest common factor. So we can only have a 2 and a 3, which, as you were told us in the chat, is 6. So how do we use these when we come to fractions? Well, if you were just given some fractions to add, I think you would automatically find, most of you would find the lowest common multiple of the denominators here. So that's how we would automatically use it to add our fractions. So we need the lowest common multiple underneath, which is our, as we said, our 480, or our 2 to the 5 times 3 times 5. And then we say, well, what do we need to multiply the 30 here by? Yeah, well, 30, we've got to hit what we need to multiply it by. What we're missing is 2 to the power 4. So we're going to have 2 to the power 4 on the top of the over our lowest common multiple. And then what do we need to multiply this side by? What's missing, thank you, Tony, is the number 5. So this is our 2 to the power 4 is 16, yeah, that we needed from the extra factors that we've got in 96 that don't appear in 30. And the extra factor we need that doesn't appear in 96 is the 5. So that's how we can use our lowest common multiples and highest common factors to add fractions. We would do that with smaller numbers. You would do it automatically, but it's just interesting to see how we can do it with larger numbers by using their factorization. Yes, so we look at these numbers here at the bottom here and say, well, we haven't done the HCF of these numbers. It's not a number you've seen already. We have to now look at 21 and 480 and see if they have a common factor. So it doesn't come out of the factors that we've looked at already. Yeah. So now we look at that and we say, well, the common factor is 3. 7 3s are 21. 3s into 480 is 160. So that is now in its lowest form.
So we have, as you all know about fractions, we have a fraction like a half, or 3/11, which when you write it as a decimal is a recurring decimal, 272727 and so on. But it also appears in many other, as it were, costumes and disguises. So look at this number 2023 over 4046. That's just a half, but it doesn't look like a half. And you've got to know the HCF there, or you've got to recognize that there is a highest common factor, cancel it down, and it's really only a half in different clothes. Okay, so equivalence classes of fractions are something that learners meet in primary school. Mathematics has many equivalence classes in it. And the beauty of it is that you just choose the simplest one to work with, but you've got to know how to choose the simplest one. Well, we know about fractions, and in other branches of mathematics, other topics, you do something similar.
So here's another clue. You've been talking about factorization. It's on your worksheet, so have a look at this. Is there a way that we could do this slightly easier? Is there an easier way? We do like to look for simpler methods, and I would suggest that you look at factorization here. Can you look at the prime factorization of those numbers, or can you find the common factors here that we can use so we don't have to get our calculators out and do this the long way? So Nellie has written on the chat what we all know as teachers, don't we, that learners do confuse the words of LCM and HCF, because the word lowest is a confusing one, isn't it? The lowest common multiple, but you're looking for a bigger number. That does strike our learners as being counterintuitive. But if they know that we talk about multiples, then it might make more sense. 7 is the highest. So once you spot that 7 is a common factor to both, and then if you'd done the full factorization, which I did when I was playing with this, I actually had 144 as 12 squared and 121 as 11 squared. And then once you take the square root, it's 12 over 11, which is 1 and 1/11, which is much easier, and you can actually do that in your head. So thank you.
So here you have some people maths. I like to do things with teachers or with learners where they get up and move out of desks and tables and actually do something practical. And here, this is about multiples too. And this star is very nice. You can do it with a pencil and paper and not taking your pencil off the paper, draw the star. And here, what you've got is, if you take one of the points of the star and follow the string around, you'll see that it gets passed across from one person to another, and it's going from in multiples of 3. So if it's behind the letter T in 2 there, it skips 1, 2 people and it goes to the third one. So this is multiples of 3. And here we've got what we call cycles. We're all very familiar with lots of cycles, like the days of the week, 7 days in the week. And when you come back to the next day, after to the 8th day, you're back on, today is Saturday, the 8th day on, and the next 8th day onward will be another Saturday. The days of the week are a 7 cycle, so are the hours on a clock. And here's another picture of a 7 cycle on the right, but the one on the left is multiples of 2, right? And the one on the right is like the teachers were doing, but this is multiples of 3. And as you go round, you can count around this, as you see, and you've got a list of numbers. Now, they're actually equivalent on this mock clock arithmetic. We talked about equivalent fractions. So naught, when we do clock arithmetic or modulus arithmetic, naught is equivalent to 7, and that's equivalent to 14, and that's equivalent to 21, just as you are, you've got the same number on the clock every time you go on 12 hours and another 12 hours. And then 1 is equivalent to 8 and 15, and the next one is 22, and so on. And these lists here, like, see the little cloud, which is a way of just making us think of something. These are the remainders when you divide by 7. So if you divide 20 by 7, you get remainder 6. If you divide 18 by 7, you get 2 7s are 14 and remainder 4. So the lists here are the remainders. So numbering points as you draw this 7-point star gives remainders when you divide any number in the list by 7. And this is going to be about clock arithmetic or modulus arithmetic. So on this picture, you see the one on the left is modulo 5, a 5-pointed star. The ones in the middle are modulo 7, and the one on the right is modulo 8, and that's the one you saw the teachers making with the string. And just as you cycle around the week, and Saturday comes every 7 days, the numbers in each list here are equivalent in that modular system. So we are today on Saturday, the 11th of February, but the 4th, the 18th, and the 25th are also Saturdays. And numbers equivalent to naught as you draw these stars are multiples of 5, 7, and 8. Now we're going to play a game. Cynthia's going to play against me. I'm going to win, Cynthia.
I'm sure you will, because I get confused with this game.
No, it's no skill. It's all luck. Right. Now, most people have played this rock, paper, scissors game, but this one's a bit more complicated. And I didn't mean to say I was going to win because I bet at it. I was just being a bit upbeat, because it's a game of chance. Okay, so will you choose to be either on my team or Cynthia's team? And Cynthia will probably win. Okay, so what we're going to do is we're going to simultaneously, we're going to choose one of these actions, and we're going to see who wins. And so if we choose the same one, we are going to draw, but otherwise you can see from the direction of the arrow which one beats which. So if you go from rock, for example, you'll see it beats sponge, but for example, water beats rock, because the arrow goes from water to rock. Okay, So have you decided which team you're going to join? So you can be a supporter or member of Cynthia's team or mine. Okay, Cynthia, ready? 3, 2, 1, fire.
Water. I'm sorry, paper. This is supposed to be paper.
Well.
You win, then, yes.
Well, if it was
Fire
water,
beats paper. Yes. No,
yes.
this is paper. I'm trying to get it flat.
I've won a point. Okay,
Yes.
again. 3, 2, 1, go. Scissors.
Rock.
Oh, you blunt my scissors. So
Yes.
we've won one
Yes.
each.
Yes.
Okay, so we'll do one more. 3, 2, 1, air.
Water.
Air and water, I've got to check that. Oh, air beats water.
It beats it. Yeah, so Tony wins.
Okay.
I knew she would.
Oh, this game is played all over the world. I've seen it in China with the, rock, paper, scissors one, where you have to step us to one side if you lose, and you have to keep stepping until you're doing the splits and you fall over and then you've really lost. Okay, so can you find 3 cycles and 4 cycles?
Sorry, Tony, and Nellie see where it says, how do you determine a winner?
You determine a winner by looking at the diagram, and as you see water, okay, if you look at water here, water beats rock because the arrow goes towards rock. Water beats scissors, and water beats, what else does water beat?
Fire.
Puts out fire.
Puts out the fire.
Okay, but if we look at water here, you'll see the ones coming in, sponge beats water because the arrow, I think that arrow goes from sponge to water. Paper beats water for some reason, and air beats water. So if the arrow goes away from that one towards the other one, you can see the one that's winning. If the arrow comes into you, then you are beaten. The arrow shoots you and you're beaten by it. Okay, so can you find different cycles in this diagram? So for example, if you go from rock, if you go from rock to scissors, rock beats scissors. If you then go to sponge, scissors beat sponge. Okay, look at sponge. And then if you go from sponge to water, sponge beats water. And if you go from water back to rock, you see that you have actually done rock to scissors, scissors to sponge, sponge to water. There's just 4 things in that, and you're back at rock again. That's a 4 cycle. Now, there's a 7 cycle round the outside, round the very outside here. Rock to fire, to scissors, to sponge, to paper. Paper beats air, air beats water, water beats rock. That's a 7 cycle. And if you look, you can find, we found one 4 cycle, you can find other 4 cycles. The traditional game was rock, paper, scissors. That's one example of a 3 cycle, and there are many more. And you can find 5 and 6 cycles as well. So why play this game? What's the point of it? Is it mathematical? Obviously you play it for fun. So why play it? Okay, well, one of the things is you can think about probability. Is it a fair game? Well, we were asked what defines a winner. You'll see with each of those elements there's the same number of arrows go in to that element. That is, it'll be beaten 3 times by 3 of the others, and it can also beat 3. So it's a 3 and 3. So it's as likely to be beaten as it is to be the winner. So it is a fair game. It is also a fair game for the rock, paper, scissors game. And cycles are fundamental and important ideas in mathematics. And we've already asked, can you spot some cycles? There's a long list of them. I want to move on because I do think this is important, because I want to tell you why modular arithmetic is important. Encrypting numbers and messages is really important in security, cyber security. And so to develop better and more secure encryption involves modulus arithmetic very often. And this is a very simple example that everybody can understand of how it works. So here's an 11 cycle. So instead of being a 12-hour clock, you've got to imagine an 11-hour clock. So when you come round to 10 and then you go back to 0, that's 11. And this is an 11-hour clock. Now, suppose you want to encrypt the number 1964, and you do it using a mapping. So you choose any mathematical rule or function you like. And my function, and you can choose anything, is you multiply the number by 3 and add 2, right? But you can have any rule, and people are not going to know the rule that's being used unless they're, unless they have that piece of information. So it would be secure. And of course you could change the rules, and as long as everybody who was involved, or the machine, the computer it was working on, knew the rule, it would be a secure system. Now, this map here is, if you start at 0, 3 times 0 plus 2 gives you 2. So you see the green arrow goes from 0 to 2, right? And then where does that go next? 3 2s are 6 and 2's 8. So 2 goes to 8. And there's another green arrow goes from 2 to 8. So 3 8s are 24 and 2 is 26. Now 26 is 2 11s, which is 22, plus 4. So 8 goes to 4. So you've got to remember this is modulus arithmetic, and we've only got these numbers involved, and that's all. So it's nice and easy to work with. And then 3 4s are 12 and 2 is 14, and that's 11 plus 3. So we go from 4 to 3, and 3 3s are 9 and 2 is 11. So we go back to 0. So we've got a 5 cycle there. And when we're doing the code, we can just use that pattern. We can use the diagram. If we do it for following the red cycle, you can see 3 1s are 3 and 2 is 5. 3 5s are 15 and 2 is 17. 17 is 11 plus 6. So 5 maps to 6. 3 6s are 18 and 2 is 20. 20 is 11 plus 9, so 6 maps to 9. 3 9s are 27 and 2 is 29, and that's 22 plus 7, so 9 maps to 7. 3 7s are 21 and 2 is 23, and that's 22 plus 1, so we get back to 1. So now we've seen how the mapping works, and what you see in the list there is exactly what you see in the 2 cycles. One is in green and the other is in red in the diagram. And of course 3 10s are 30 and 2 is 32, and that's 22 plus 10. So 10 just maps to itself. So it's not actually going to be used. So supposing I encrypt 1964, well, you see that 1 maps to 5. So the first number is not sent as a 1, it's sent as a 5. 9 maps to 7. So the second number is sent as a 7. The 6 maps to 9. So the third number is sent as a 9, and the 4 maps to 3. So instead of being interpreted as 1964, it's sent as 5793. And then when you're decrypting it, you just use the reverse mapping, and 5 goes to 1, 7 goes to 9, 9 goes to 6, and 3 goes to 4, and you get back to the number you started with, the 1964. So that was just a very simple, just to give you an idea. And when you make it more complicated, there's something called error correcting codes, which when the messages, complicated, long messages are sent, that they automatically detect errors and correct it. So there is very simple use of mathematics for you. Of course, when it's actually being used in cybersecurity, it's not quite as simple as I'm making out, because you're sending much longer methods, but it's actually using a use for modulus arithmetic. I want you to work out what is the highest common factor of those two algebraic expressions. You need to factorize them. So we're going to be doing factorizing, but a little bit of algebra here. What's the lowest common multiple? You're going to need to be factorizing them, and remember what we did about multiples. And then there they are, and add up those two fractions. So adding algebraic fractions. Adeboyega has put it on the chat that the highest common factor of these two expressions is x minus 2. When you factorize them, you see that the first one is the difference of two squares. X squared minus 4 is x plus 2 times x minus 2. And the other expression, quadratic, factorizes into 2x plus 3 times x minus 2. So that common factor, and yes, you've been saying your learners find it difficult. Emphasize that it's a common factor you're looking for, and not, don't place so much emphasis on the h. Say you're looking for the common factor here, but the highest one, and it's x minus 2. And then what about a multiple of both of these? What is that? What is the lowest common multiple? Well, it's got to be something that both of these two numbers are factors of, but you're not going to repeat that common factor. You're not going to put it in twice. And so the lowest common multiple is 3 times x plus 2 times x minus 2 times 2x plus 3. Now, when you come to add the fractions, you need to think of the factors, and it's useful to be thinking of the lowest common multiple, because that's what you put on the bottom. Now, sometimes people just multiply both those numbers in the two denominators together, and they get a much bigger number on the bottom and cause themselves a lot more work. And that's why we're encouraging the fact that you find the lowest multiple, the lowest number that is a common multiple of the two numbers on the bottom in the denominator. So when you add them up, then the 3 times x squared minus 4 needs to be multiplied by a 2x plus 3. See, you're doing something exactly like we were doing with numbers. And if you can add fractions with numbers, you can add them with algebra. But we find that learners everywhere in the world seem to struggle, don't they, with fractions. So it is something that we have to pay a lot more attention to as teachers, and ask ourselves why it's so difficult, and try to help learners to understand why it works, and then maybe they'll be able to do it. I mean, the most important thing is to be able to do it for the algebra, really, because they can do it on their calculators with the numbers. So for the second fraction there, of course, they haven't got a 3 or an x plus 2 in the denominator, so we've got to multiply by 3x plus 2, and when we simplify that, we get 5x plus 9 on top, and there's no common factor there. So there's the result there. Over to you, Cynthia.
Okay. Well, now we're moving to a slightly different way of looking at it. We've trying to find this time all the factors of 360, not just the prime factorization, but every single possible factor that goes, any number that goes into 360. Now you can imagine there'll be quite a few. So we want to have a method that makes sure that we find them all and we don't leave anyone out. So we need to be systematic and quite clever in how we do this. Now this diagram is on your worksheet. So if you've got your worksheet handy, have a look at it. We want you to start to fill it in, but I will just try and, as it's quite a large, complicated diagram, I want to talk you through it. We know that 360 is 2 made up, it's 2 cubed in its prime factorization, 2 cubed times 3 squared times 5. So we know that 2 and 3 and 5 are going to be factors. We can probably see that, yes, we're probably going to have 9 plus 3 squared, and we might have 4. So, you know, we can make some guesses, but we want to be systematic. So we're going to take the first factor in this string first and say, what power of 2 could I have? I could have 2 to the power 0. That's 1. That gets us our 1 in there. Or I could multiply by 2 to the power 1, or 2 squared, or 2 cubed. So you start off imagining a tree in your head, a tree diagram. Yeah. So with the first set of options on the left, you know, your first 4, and if you look at the left-hand column of the table, you'll see in that first left-hand column, we've got different powers of 2. And then you go along your tree diagram. So the next option will be the powers of 3. And then the third option will be your powers of 5. Yeah? So if we look at the first column, the powers of 2, we've got 2 to the 0, which we know is 1. 2 to the power 1, which is 2. 2 squared, which is our 4. And then underneath 2 cubed, which is our 8. But if we start off with 2 to the power 0, the next option we could multiply it by is either 3 to the 0, 3, 1, or 3 squared. If we choose to multiply 2 to the 0 by 3 to the 0, we could also multiply it by 5 to the 0, and we get the answer 1. Or if we get here, we could multiply it by 5 to the power 1. So we get 1 times 5, so we get 5. And then our next option, still with 2 to the power 0, is we could have multiplied by 3. And then our third, we could have then done 5, 0, 5, 1. So just spend a few seconds looking at the diagram and trying to fill in the gaps to make sure that you really understand the structure. But it isn't, in essence, it's just a tree diagram made a little bit easier for you to read. If you can imagine trying to draw a tree diagram with all these options, you just would get in such a muddle. So we need to be clever and use a table. And this way, as you see, we're being very systematic. And hopefully by doing it like this, we won't have left out any factor at all. So this is a way of finding all the factors, not just the primes. Right, so we moved on a bit quickly along, so I say you just see how it works. So this is the table now filled in. And if you now look down the very last column, yeah, you'll see they're not in order because of the way we set the structure up. So we started very systematic with all the 2s, followed by a combination of 3, followed by 4, 5. So we don't have them in order. We could rewrite them in order, as you see at the bottom, there it is. But this way we can still be absolutely sure that we've got them all. But not only that, we can work out how many we should have. Because if you go back to the beginning, our diagram, we've got 4 options for the first number. Yeah. Remember, we're multiplying some sort of power of 2 by a power of 3 by a power of 5. So our first option, we have 4 different powers. We could have 2 to the 0, or 1, or 2, or 3. So we've got 4 options. Followed in the next, after the next branch, we've got 3 options for each of those 4. So we've got 4 times 3. And then the 5s, we only have 2 options. So we've got 4 times 3 times 2 possible factors. And if we multiply that together, we find out we should have 24. And if you count the rows as you go down, hopefully you'll find there's 24 rows in our column. Thank you, Tony.
There is. So we're going to go do this with all numbers, big numbers, and generalize what Cynthia's just been doing with 360. And think of this, when we're doing it, we're going to think of the tree structure for the factors of 360, and then think of the same general idea for more factors and bigger factors. So we're going to have here 12 questions.
Yeah, that's me. Yes. So yes, we've got 12 different questions that between us, Tony and I are going to take turns, I think, to answer some of these with you. So remember, we're not, yeah, I'm going to say we're not just looking at prime factors this time. We're emphasizing it must be all the possible factors. So for 20, you see here, it's got 6 factors. 2 of them happen to be prime, but the other 4 are not.
And we're going to take these questions one by one. We're just setting the picture now. Okay. So the first question is, how does a number 1 behave in the world of factors? So 1 is quite special, really. It's a factor of every number. So only number which is a factor of every number, and it isn't prime and it isn't composite. And you may ask, why isn't it prime? Well, I'll come back to, I'll answer that in a minute. It's also very special because when you multiply anything by 1, you just get the same number again. It doesn't change anything. So 1 is what we call an identity. So that's another way that 1 is special. Now, what can you say about numbers that have exactly 2 factors? That's prime numbers. Prime numbers are numbers with exactly 2 factors. And 1 doesn't have 2 factors, so 1 isn't prime. So the prime numbers have the number itself as a factor and 1 as a factor. End of story. So, for example, the factors of 7, which is prime, are 1 and 7.
Right, so now what about square numbers? How many factors do square numbers have? Well, the answer is 3. When, and this is only when, the answer is 3 if the number you're squaring is a prime number. Yeah? So the square of a prime number has 3 factors. But if the number's not a square, not a prime number, if we're squaring a number, the example there is 14, then we find that it has, because 14 is not prime, it's made up of 2 squared times 7 squared, and it has 9 factors. But I think what we do say is the thing they have in common is they both have an odd number of factors.
We've slipped in the word composite there, which I don't think we'd had earlier. We might have done, but composite number is a number which isn't prime. Okay, it's got well, it isn't prime and it isn't 1. It's got more than 2 factors. Yeah.
So what about cube numbers? Right, that's the next thought. Well, let's have a look at the cube of prime numbers. So if 2 cubed, for instance, yeah, then 2 cubed has 4 factors. But if they're composite, in other words, not prime, and the example that Tony's given is 6 cubed, then that's got a lot more factors. So when you're doing these type of things, if you're doing this in class, you really do need to keep a track of different numbers. If you've got your learners, for instance, I often get mine to find out how many factors all the numbers from, say, 1 to 20 or 1 to 25 or something, depending on the size of class and the groups I've got. You've set them to find how many factors these numbers have and keep a record, because we need to know, as we're going through this, we're giving you lots of information that sometimes they have this number, sometimes that. So you need to keep a record of these. We obviously haven't got time for you to sit and do them all today, but it's a lovely exercise to do in class.
Did you tell me that when you were teaching before you retired, you used this particular question?
Yes, that's what I was just saying. But I definitely have done it many times, and with up to grade 9, that sort of grade 8, 9, that to get them to list them all and look at them. We didn't get as far as the rules. We didn't get as far as the counting principle, but they understood that different numbers had different, and they could pick out the commonalities, like the cube numbers and the square numbers. So it was interesting for them to just put forward their own theories as what they thought was happening.
So what about numbers with 4 factors? What do they have in common? I mean, we've just looked at something, but we've got the cube of a prime number, and like 2 cubed, which is 8, that's got 4 factors, but 6 has also got 4 factors, and that isn't prime, it's 2 times 3 is 6. So the 6 has also got 4 factors, 1, 2, 3, and 6. So in general, and it's in red at the bottom of the page there, if you've got a prime number A, then it will have 4 factors. The 4 factors will be 1, A squared, and A cubed. But if you've got 2 prime numbers, A, B, multiplied together, there'll also be 4 factors, 1, A, B, and the product A, B. So there you go. That's the general idea.
So this is why I said you need to keep some, as you're working this out, because we now say we'll give some examples of numbers with 5 factors, and what do they have in common. So here are some that we've got, 16 for instance, and what we find if you were doing more investigation with different numbers, that you would find other prime numbers to the power 4, so 3 to the power 4, 5 to the power 4, and so on, also had 5 factors. But you would need to do the investigation to find that out. At the moment, we say we're skipping this rather fast.
But you can see that this is that it will have 5 factors.
Yes, I've got to say this is what we hope they do.
They're 2 to the 0, 2 squared, 2 cubed, and 2 to the 2 to the 4. And if it was 29, which is prime, okay, to the power 4, it would be 1, 29, 29 squared, 29 cubed, and 29 to the 4th. So it's very easy to see that the 4th power of a prime will always have 5 factors. So what about numbers with 6 factors? Okay. Just pause for a minute there and let you think. What numbers are going to have 6 factors? Yes, I'm sure you thought you decided, because we've done so many like this, that 2 to the 5th and any power of any 5th power of a prime will have 6 factors. Okay. But if you track back a bit and have a square number and a prime number, that will also have 6 factors. And there's an example for you. 4 times 3, which is 12, and 4 is a square number, and that's 2 squared. And 12 has those 6 factors. 1, 2, 3, 4, 6, and 12. So there we are getting, I think we should be beginning to get a pattern, a picture here. And when we're looking at the powers in the prime factorization, how we can use those powers, just as Cynthia was explaining with 360, how we use them to find out the total number of factors all together. Sorry, I got back there. So all the numbers with 6 factors are either the 5th power of a prime or the product of a square number and a prime number. And when you come up to product of 3 prime numbers, 2 times 3 times 5, for example, you won't have 6, you'll have more factors. You've really got to, when you start bringing in more primes, you bring in more factors.
Combinations, really, you can combine them in different ways, can't you? That's
right. But it isn't the case that when you've got a bigger number, it's definitely got more factors, because it might have it might be big because it's got some big prime factors, and it's still only got a few factors altogether. So let's look at the results so far. Cynthia.
Yeah. So what do we notice about these numbers with 2, 3, 4, 5, and 6 factors? Well, say we've gone through the 2 factors are definitely numbers that are prime. 3 factors is the square of a prime number. 4 factors, the cube of a prime number, and as we went on with 5 factors was the 4th power, and so on. So we know those, but we've got some extra ones that with 4 factors, because we can also not just have the cube, but have the multiple of 2 primes when you multiply 2 primes together. So there's the 4th power for 5 factors, the 4th power for prime, and 6 is the 5th power, and so on. And we found some other examples of 6 somewhere, haven't we?
So
yeah, 4 times 5. Yes, that's how I've got my it was obscured on my screen as well. So yes, the product of 4 is a prime squared. Right? So remember, that's a square number times a prime number, also has 6 factors.
And what we want you to do here is to look for patterns when you're doing it with the sort of thing with learners. Keep sort of, well, it should be come to them so much. You send it off to them, they know, oh, if we look for patterns, we'll probably be able to see some patterns which will help us do this. So the big question is, how many factors? So what we're going to do is use what we have done so far to answer some questions about numbers with more factors. So this is a question: what is the smallest number with exactly 14 factors? So we've leapt from 6 to 14 because we think we've sort of got a grip on the idea of what the patterns are. So building on what we've done, we know that n to the 6th of n is a prime number, has 7 factors, n to the 7 has 8 factors, n to the 8th has 9 factors, and so on for any prime number n. So a prime number to the power 13 will have 14 factors. But also, because 14 factorizes into 7 times 2, numbers with 14 factors are either of the form a prime number to the power 13, or one prime number to the power 6 times another prime number, a to the power 6 times b to the power 1 for primes a and b. So we can find numbers with 14 factors this way, but the big question now is, what is the smallest one? So if we want to get a small number with 14 factors, we want to get our a and b to be small. So obviously we want to choose a and b to be 2 and 3, or just 2, but 2 to the 13th gets very big. Whereas if we are multiplying 2 to the 6th by 3, it's very much less than multiplying 2 to the 6th by 2 to the 7th to get your 2 to the 13th. So I've listed the factors of 192, which is your 2 to the 6th times 3, and you will see this is not written as Cynthia was showing you with, as we did with a table with 360, because it's a little bit simpler than that. We've only got 2 numbers involved here, so I thought we could just write them out there, and you can see there's 14 factors, and 192 is actually the smallest number with 14 factors. But some other numbers with 14 factors are 2 to the power 13, and that's 8,192. And I can swap over the 2 and the 3, and instead of having 2 to the 6th times 3, I can have 2 times 3 to the 6th, but that's going to be bigger because 3 is bigger than 2, obviously there. Okay, so let's move on to another question.
Right, so if you know the prime factorization of a number, how do you find the total number of its factors? We should have had lots of clues by now. So, right, for example, Tony, can you click the button with 12? Oops, 12 is, we know has 6 factors, and we know it's 2 squared times 3. 15 has got the 4 factors. So remember, look at the primes. We're looking at primes the whole time. 32, remember, 5th power has 6, of a prime has 6 factors. 72, it's got 12. What's the connection here? Remember, we went when we did that big diagram of 360, we started with 2 to the power 0 because 1 is a factor. So we need 2 to the power 0 as well as 2 squared, 2 cubed. We need 3 to the power 0 as well as 3 and 3 squared. So what do we do to those numbers? How do we get 12? Can we have spotting patterns here? Right, 2 to the 5th plus 2 to the power 0 here and 3 to the power 0. How do we get 12?
Okay, so what this is all about is the fundamental counting principle. It's a rule used to count the total number of possible outcomes in a situation. So supposing there are m ways of doing something and there are n ways of doing something else, then you multiply those two together, m times n, to perform both for the number of ways of performing both actions. So if I'm going to be choosing to put on a blouse or a top and trousers, and I've got 3 different tops to put on and 2 different trousers, and I'm trying to decide which. So with each of my tops, I can put on one or the other pair of trousers. So I've got 6 possibilities, 3 times 2. So that's the fundamental counting principle. And if we have more than more than 2 different things that we're doing. I mean, if I was also choosing what shoes to wear, you know, then we'd multiply the number of ways of doing each action. So that's your fundamental counting principle, and it's what we use here. So here is the general formula at the bottom of the page, and what we've got to remember, well, it might help to remember, is what we did with 360, that the 2 cubed can contribute to the factors in 4 different ways, 3 in 3 ways, 5 in 2 ways. So altogether we get our 24 factors there. So what this is, how it works, how you get the general formula, and this is the proof of the general formula. So if you've got any prime factorization at all, where the prime numbers are a1, a2, a3, a up to an, and the general one is ar, and those prime numbers are raised to the power a1 to the power p1 times a2 to the power p2 times a3 to the power p3 times it, and then a few more, and then AR to the power PR, and then a few more, and then AN to the power PN. We've got these prime factors from R is 1 to Rn. Don't be frightened of the algebra, it's how you write it down. When you were 4 years old, 3 years old, you didn't know how to write, how to write language down on paper. It's similar to that. This is how you write mathematics down. Okay, and we're learning in school how to write the mathematics in formulae when we need to. So AR contributes either AR to the naught, or AR to the power 1, or AR squared, or any power of AR up to AR to the power PR to the factors. So there's the number PR plus 1 in that number of different ways. So the number with that prime factorization, just copied from above, has P1 plus 1 multiplied by P2 plus 1 multiplied by P3 plus 1 right up to that product Pn plus 1. So the rule is you look at the powers in the prime factorization, you add 1 to those powers, and then you multiply those numbers by 1, and that gives you the total number of factors. Okay. So we've dealt with the fundamental counting principle.
Yes, so using those ideas, we can answer lots of quite interesting and quite big questions here too. So the question that we've got at the top is, what's the smallest number with exactly 100 factors? Or the other question 12 on our original list was, which number less than 1,000 has the most factors? So thinking about the top one first, the smallest number.
We're going to ask you, we've got some time now, We've
Yes.
been doing a lot. Cynthia and I have been telling you a lot of things. And what I'd like us to do is to now give you time to do something, because you've been doing a lot of listening. So we want you to do some more maths and some thinking and
Yeah.
some participating. So would you like to answer those 2 questions, please?
Yeah,
Think of
all I was going to say, all I was going to do, Tony, was just point them into the direction of the fact we want as how many factors. We want 100 factors, so we've got to think of the powers of the factors that we're dealing with, haven't we? Just reminding them we're talking about powers. So how many powers do we multiply together to get 100?
And then you can use the worksheet as well. You can copy bits from it if you want to with your learners. So, and then there is this how many factors on the Aiming High website, which has got lots more, well, not a lot more, but all this sort of thing with a worksheet and some suggestions for teaching and so on. So anybody, now you're trying to get a small number with a lot of factors. So how are you going to do it? What's the power going to be if you're going to have 100 factors? Just generalize what we've been doing and think if you can use what you've just learnt. The smallest factor, prime factor, is what? You know what the smallest prime number is. So we're going to make use of that. If you want to keep the answer to be small. And what power would you have to raise it to? So my hint to you is use the smallest prime number 2. And what power do you have to raise it to get a big number? Of course, it's going to have to be a big number if it's got 100 factors. 2 to the power 99 is the smallest number with exactly 100 factors. The number will be bigger if it has factors 3, 5, or other primes. Okay, so there you go. Well done. Well done, Provia. 2 to the 99 is the smallest number with exactly 100 factors. Now, which number less than 100 has the most factors?
Less than 1,000.
Less than 1,000 has the most factors.
So sort of the opposite way of thinking now. The first one was the smallest number, and now we're looking for the most factors rather than the fewest, aren't we?
Rather than a small number, we're looking for a number with a
lots of factors.
Lots of factors, but still keeping it under 1,000.
Yeah. I suppose the hint is, Tony, if you use just one prime to get, well, you said there the number would be bigger if it has lots more factors. So that's the clue, isn't it? If we want a lot of factors, we've got to have a lot of primes in there somewhere.
You want lots of factors here, so you want it to be the product of quite a few prime factors and not get too big, because it's got to stay under 1,000. But this is a nice challenging question for FET, for that is for those of you who are in other countries, for upper secondary. It's a nice challenging question for young people who are doing well, high flyers, and you want to give them a challenge that they can get their teeth into, not too routine and easy. They need to think about it. So this question has got a long history, as Cynthia has been retired a while, but she didn't do this during the sort of AIMSEC era only. She did it from Enrich originally, and Enrich was a website which I set up almost 30 years ago, not quite, nearly 30 years ago. And on that website, we only published children's solutions, not our own solutions. And I have a lovely solution to this from children, okay, to this particular question from from children, and I more or less copied it on the next slide. And if you go to the Enrich website, you will see how many factors appears there, and then I've changed it a bit and added to it. 512 somebody is suggesting, and somebody else has done 840. 512 is my guess too, from Provia. Akin Sharinwa says 540. 360 has also been offered up. So we're getting lots of suggestions now. Well done, everybody who's ventured an answer. The answer is amongst those, the right answer. So here goes. This is what you've got to do. You have to get a lot of factors. So you have to try and multiply together the widest range of prime numbers, starting with the lowest. So if you try 2 times 3 times 5 times 7 times 11, you get a product that's bigger than 1,000, and you're trying to keep it to be less than 1,000. So you can't bring in 11, that's too big, but 2 times 3 times 5 times 7 isn't as big as you can get it. It only gives you 210. So you can take more powers of that 2. And so if you want to get near to 1,000 without having to shoot over the top, then you want to put in 2 cubed. So if you put in 2 cubed times 5 times 3 times 5 times 7, you get 840. So as Joshua's just put up there, 840 is the answer here. It's the number which the most factors, the number less than 1,000 with the most factors. It's got 32 factors altogether. Okay, so we've reached the point here where we just bring back to remind you of lots of little images of all the different things that we've been doing today. And you'll see there in the box, it's pink. How do you find the total number of factors without listing them? For example, 15,552, which is 2 to the 6th times 3 to the power 5. You add 1 to the 6 to get 7. You add 1 to the 5 to get 6. You multiply 7 times 6, which is 42, and it will have 42 factors. That's just an example of what we've been doing, using, again, or based on the fundamental counting principle.
I would find it was the adding fractions, algebraic fractions, using the LCM and HCF. I was like you suggested previously, would have just done the multiplying by both and ended up with enormous algebraic multiplications to deal with. I think that would have been my go-to method. But so thinking about factorizing and finding the lowest common multiple was not something that I had previously thought of doing with algebra. I would happily do it with numbers, but that was a revelation. I mean, it makes perfect sense, but I just wonder why I would not have done it. Because you can end up, as you say, with loads of algebra that people can easily miswrite or misread and end up with the wrong answer by just having too much algebra to do.
Like, I love the way you are describing the pattern of factors here. I like the way you are describing it.
Yes, Nella Seaway says, I was so challenged by how many factors. Eva says, may I please have the answer for number 11?
Number 11, I'll hunt that out.
Number 11, I'm going to go back.
Oh, the smallest number with exactly 100 factors. 2 to the 99, that was the one.
Yes.
Back one.
There we are.
There you go, yeah.
So that, Eva, is the answer, 2 to the 99. It's the smallest, it's got 100 factors because it's 2 to the power 99, and because we've kept to the smallest prime number, that's the smallest one you can possibly do.
I was going to say, I'm with her, Tony. If you remember, I queried this, didn't I? I said, why couldn't we have 2 to the something times 3 to the something, and with smaller powers, and because you intuitively think maybe that might come out smaller, but you get a big shock when you try.
Yeah, well, that's the interesting thing about this is the exponential function. It is amazing how when you go to higher powers, how much bigger the number gets. And so, yes, so there's your answer there. And so now going back to the collage here, so Akanashima says, I love how to add fractions that has quadratic denominator. Thank you for this problem.
Yes, certainly. I think they'd be very useful. Some of the, I find it particularly interesting, the number of factors in a number. And it rings a bell from a long time ago. But in recently coming into teacher training, I had forgotten it. So I think that was really useful and fascinating. So I'd certainly use that. Well, I thought it was interesting where somebody mentioned that highest common factor and lowest common multiple can be confusing for people. And I understood his point. And I also saw a survey from online tutors that they said many of their tutees found it the most difficult topic in GCSE. So that does seem a common misconception that people just struggle with the concept, because I suppose there is a counterintuitive element to it. So when teaching it, I'd certainly try and get it across what Cynthia said, that although it's the lowest common multiple, it's the numbers, because they're multiples, emphasize that they're multiples, so they're going to be greater than the two numbers you're dealing with.
Yes, I think it's the stressing the multiple and factor that and of those, it's so often abbreviated to HCF and LCM that learners don't know what the
they lose track of the idea. They just see initials, don't they, and don't realize that it, as you say, it's multiples and it's factors, and that's what we need to emphasize the whole time.
Yeah,
I hate acronyms.
Yeah, I think that's we do them no favors by writing those initials.
Cozy says, I love how we count factors using exponent. It's interesting. And Ahmed says, I like how we count factors using the prime factors. It's so simple and easy. Nella Seaway says, I will definitely use prime factorization when adding fractions with my grade 8. It's year 8, grade 8. Okay. Kemi says, I find the modulos interesting, particularly the application with encryption. And there I'd like to say, I do think whenever you can, you should refer to either how the maths is used in other school subjects or how it's used in the real world. And if you can find a simple thing that you can do in class that illustrates it, like I just did with you about the modulo 11, they begin to see, well, I can see that could be very, very useful. I can see how that could be a secret code or an encryption that we could use. Yeah. Okay, so I'm going to then now move on to tell you what we have got in store for you for the next few months, for the remainder of the year. Next month, it's the 25th of March, when we're doing some geometry on properties of quadrilaterals. And the next one, April, is trees and contingency tables. And then in May, we're going to be doing mean, median, mode, and range averages, and so on. You can see that for yourself. We are doing these few to very fit in with the courses we're teaching in South Africa. So I hope to see people who are doing our courses in South Africa at these workshops, but also more teachers from anywhere who are interested in joining us. You're very welcome. Olalifle says, I never understood the rock, paper, scissors game until today. And just playing it with 3 things, rock, paper, scissors, is enough. It's still a great game, and it's a game you can play if you've got children in your family with them, which they'll enjoy. So great job to our resource persons. I've learned factors in a special way today. Somebody else says, I'm really glad that you found it interesting. Now, what we offer you, AIMSEC offers you, is lots of learning packs. And each of these learning packs has a PDF of the worksheet, templates with instructions for making resources. It has videos, notes for teachers. And in the notes for teachers, you've got solutions, curriculum links, learning objectives, diagnostic quizzes, suggestions for teaching, key questions to guide learning, and follow-up ideas and links, all those things there. And we have what we call inclusion guides for school and home learning. And the inclusion guides have a starter activity for everybody to do together. Then they've got a collection of learning activities to suit all ages, but on the same theme. And then they've got solutions and suggestions for teaching and assessment. So do look at our Facebook page, where you'll see a different one flagged up each day. Do look at our Aiming High website, which has got a search, and you can search for the topic you're going to be teaching next week and find quite a lot of learning packs on that topic, I hope. And there is the website address, Aiming High. Just remember, Aiming High. I hope you'll use it and find it useful.
Right, and these Tony has already flagged up Aiming High as the place to go, but these are the specific links which you will get, and when you get the copies of the slides, that you can then follow up what we've done today. How many factors was the big one? Easy Calc, if you remember, that was the square root. Multiples, shading in the multiples, which led on to the prime sieve. The path to the stars, that again was the modular or the clock arithmetic, and then the scissors, paper, rock game. So all of those that we've featured today are easily available. Go there and you'll get more information. And then last but not least, or last two, the YouTube channel and the GTEN website, all resources that we definitely encourage you to have a look at.
We try to put all our GTEN workshops on YouTube, and also the GTEN website we're developing this website. It's quite a small website at the moment. So we've reached nearly the hour and nearly the time to say goodbye. There's a few more links here. We do hope you will find the Aiming High resources useful. And thanks for participating. We're glad that you came along on a Saturday evening, or a Saturday morning if you're in America, Maryland. So goodbye until the next GTEN workshop, and that's going to be on properties of quadrilaterals. There you see a picture at the bottom of the screen of sorting out little cards, a card sorting exercise, which is for formative assessment. So goodbye from me, and we'll hope to see you in March.
Thank you, Tony and team. Thank you, everyone. Bye.
Yeah, bye. Bye, everybody.
Bye, everyone.
Bye.
Bye. Bye. Bye. Bye.
Bye, Tony.